Hi all. Today we discuss some theorems on the higher order derivatives, partial derivatives. If f of xy and its partial derivatives fx, fy, fxy, and fyx are defined throughout an open region containing a point AB and are all continuous at AB, then you can evaluate the difference, the partial derivatives of f with respect to x and then y at AB, that will be same as the partial derivative of f with respect to y then x at AB. That means if this partial derivatives fx, this fx stands for the derivative of f with respect to x, partial derivative of f with respect to x, and similarly fy represents the partial derivative of f with respect to y, and f xy. Okay, so this is the derivative of d by dy of df by dx. So that is a representation for fxy. So that is equal to dose d square f by d y dx. Okay, so differentiate with respect to x first, then y. Similarly, you can define dyx. This theorem states that the order of the differentiation can be changed. If you evaluate this fyx, then you can evaluate this fyx by evaluating the derivative of f with respect to y first, then with respect to x. When you evaluate this, you represent this as d square f by dx dy. These two quantity will be same if you have this hypothesis. That means fx, fy, fxy, and fy are defined and continuous. Okay, so if it is not easy to evaluate fxy, then you can try fyx instead of evaluating fxy. So we can let's see an example for this. We can verify the partial derivatives, mixed derivatives of this function w, that is equal to xy plus e raised to y divided by y square plus 1. So first you evaluate this dou w by d uh, y first, that is equal to x, that is the derivative of xy, that is x plus the derivative of e raised to y by y square plus 1. So that can be obtained by using the quotient formula, y square plus 1 derivative of this quantity, y square plus 1 into derivative of e raised to y, that is same as e raised to y, minus the numerator into the derivative in denominator, that will be 2y into e raised to y whole divided by y square plus 1. So this is the derivative of w with respect to y first, then find the differential of this dw by dy with respect to x, then you can get dw by dy and derivative of that is equal to, this is with respect to x, then that will be 1, and the next term there is no x in this expression, therefore the derivative with respect to x is 0, then that will be 1. Okay, so this is the one way to evaluate d square w by dx dy, that is nothing but fyx. But if you evaluate the other way around, say dfxy, that is equal to d square w by dy dx, that is equal to d by dy of dw by dx. When you evaluate the derivative of w with respect to x first, then you can get d by dy of, the bracket will be the derivative of this expression with respect to x first. Since the second term does not contain any x, you can find the dw by dx as the x itself, that is y itself, that is not x, that is y itself, then the derivative of y with respect to y is again 1. So this is the easiest way to evaluate this mixed derivative. So this is the idea of this theorem. You can find the mixed derivative in any order if these hypotheses are satisfied. So since the proofs of this theorem or the rest of the theorems, the proofs are not included because that is beyond our scope of the syllabus. So you need to understand what is this the statement of the theorems. So this is the theorem 2 and this is the illustration of that. Next we have a question. This is a problem. Find f, y, x, y, z. This is the this f, y, x, y, z represents the fourth order partial derivative of this f. First we evaluate the derivative of f with respect to y first, then followed by x, then followed by with respect to y of that expression, and followed by that we differentiate that expression with respect to z. So this represent it is denoted by d4f by dz dy dx dy. That means first you evaluate with differentiate with respect to y, then with respect to x, then with respect to y again, then with respect to z. So we need to evaluate this. So first we evaluate fy. Fy is the derivative of f with respect to y. So the derivative 1 is 0, so the first term will be 0. The second term we can consider 2xz are constant, so you can write it as first z, then the derivative of is y square, that is again 2y, plus the derivative of x square y. You can take x square as the constant, then derivative of y is 1. So this gives the expression minus 4x y z plus x square. Okay. Now you evaluate fyx. What is fyx? Differentiate fy with respect to x. So differentiate this expression with respect to x by taking y and z are constant. So minus 4yz are constant. The derivative of x. Derivative of x is 1. So that is the first derivative of the first term, and derivative of the second term. So that is 2x. Okay. So this will give fyz. Now fyx. Now you evaluate fyx again y. So that is equal to differentiate this expression with respect to y again. So by taking 4 and z are constant from the first term, then that will be 4z plus there is no y in this expression, the value is 0, that is minus 4z. Now you evaluate fyx yz. So you will differentiate this expression with respect to z. That means differentiate this with respect to z by taking minus 4 as a constant, then this will be the final answer. So in this manner you can evaluate the partial derivatives of any function, any higher order partial derivatives following this rule. This is the next theorem, the increment theorem for functions of two variables. This is analogous of the theorem in the one variable system. Suppose that the partial derivatives of f of x comma y are defined throughout an open region and containing the point x0 y0, and the partial derivatives df by dx and df by dy are continuous at x0 y0. Then the change dz, we consider z is equal to f of xy. Then the change in this function f of xy is defined as f of x0 plus delta x y0 plus delta y minus f of x0 y0. This is the change in the function z in the value of f that results from moving from x0 y0 to another point, another nearest point x0 plus delta x comma x0 plus delta y in R, satisfying the equation delta z is equal to this expression, in which each of this epsilon 1 epsilon 2 tends to 0 as both delta x and delta y tends to 0. So this is the definition of the change of function, two variable function z equal to f of xy. So there is no proofs of this theorem. We have not included the proofs in the syllabus, so you just understand this statement of this theorem. Once you define the change in this z, then you can define the differentiability of z. This z equal to f of xy is differentiable if this holds, this theorem holds. That's the idea of the definition. Definition differentiable function of two variable. Okay? So if this happens with epsilon 1 epsilon 2 tends to 0 as both delta x delta y tends to 0, then we call this as the differentiable function. So this is the definition. This is the corollary of the previous theorem. Continuity of partial derivative implies differentiability. So you must understand this theorem and statement of this theorem. You need to by heart the statement as well. If the partial derivatives fx and fy of a function f of xy are continuous throughout an open region R, then f is differentiable at every point of R. So we are not going to prove this corollary, but we need to by heart or understand the statement as well. This is the last theorem of this section, section 4.3. In this section, we have differentiability implies continuity. If a function f is differentiable at x naught, y naught, then f is continuous at x naught, y naught. So this gives a sufficient condition for the differentiability. If differentiability holds, then we can say that f is continuous. Okay, so this says that this corollary of theorem 3 states that the continuity is not enough to get the differentiability, but if you have the continuity of fx and fy. Okay, so here we assume here we conclude the continuity of f, not the partial derivative continuity of the partial derivatives. Here the continuity of along with the continuity of f, we need to assume that the continuity of the fx partial derivatives df by dx and df by dy in order to get the differentiability of f. Okay, so the converse is trivial. If f is differentiable, then f is always continuous. Okay, so if you consider theorem 4, the converse of the theorem 4 is not true. Okay, this is not enough. The continuity of f is not enough to get this f is differentiable. Along with the continuity of f, we need to get the continuity of the partial derivatives as well to get this differentiability. So with this we can conclude section 4.3. The next class onwards we will discuss the next session 4.4 that deals with the chain rule of the partial derivatives. So before going to the next session, you need to explore the following problems. You try to find out the answers of the following problem. In each of these functions, you must evaluate the partial derivative of f with respect to x and partial derivative of f with respect to y, and partial derivative of f d square f by the second order partial derivative with dx dy. That means for this we differentiate with respect to y first, then x. Then evaluate f y. This is f x y. So this represents d square f by dy dx dy. Okay. This is nothing but d square f by dx first, then dy. Okay. So you evaluate all of these partial derivatives for these functions. So this can be this is your exercise.